Science, the only site on the internet that does physics. Everybody else moves concepts around. And here we move objects. A rope is an object. A thread, I don't know if you can see that, it's an object. We only move objects. It's when you start moving concepts around like energy and mass and stretching the field and transferring the information. That's when it gets very scary. Some people even move the counter space. I usually move my beer from the counter before they move the counter space. Anyways, today we're going to talk about this subject, the God particle. Now, how's that for a subject matter? That's getting close to heaven, okay? The God particle. And this was proposed by this gentleman. His name is Peter Higgs. Won a Nobel for that. So that's the subject matter of today. If you have something better to do, well, then don't do it. Stick around, you might learn something. Okay, so what is this God particle? Well, it's the Higgs boson. I call it the Higgs bozo. But it's okay, the Higgs boson. And it's a particle of mass. So before you can understand what the Higgs boson is and why this man, Higgs, won the Nobel Prize and why his name was used to give a name to this particle, you need to know a little bit about mass. What is mass? Okay. Now, we all know what mass is. I mean, everybody who went to high school, secondary school, right? We all learn it in the first couple weeks. Mass is the quantity of matter. Mass is either the quantity of matter or a measure of the quantity of matter of an object. Very simple, very straightforward. In fact, here you have the high school version by two prominent sites, so we have a little authority here, right? First one, mass, how much matter there is in something. Matter is anything you can touch physically. And the quantity of matter contained in an object by the Einstein's world of physics. Open and shut case. That's what you learn in high school. And since 99% of the people never take physics, they never want to touch the subject ever again, that's what they come out of high school with, and this is what they repeat, and they say, yeah, it's the quantity of matter of an object. We're done. Not really. Not quite, okay? Here we have a little authority, okay? Just so we always put authority behind everything because I want to make sure that people believe in authority, okay? Here we have two very authoritative people. One is John Wheeler, Edwin Taylor. And Wheeler for sure is known by a lot of people out there. And they say nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass. Now, isn't that incredible? Here we have on the one hand, on the left, we have it's the quantity of matter. And on the right, these people say, no, that's not mass. That's a pretty inauspicious start for a theory that's going to propose a particle of mass. We don't have any idea what mass is. Keep in mind that Wheeler and Taylor, they're not telling you what mass is. They tell you what mass ain't. Okay, they say, no, quantity of matter, that's not mass. Not at the college level. Maybe at the high school level, for the peasants, yeah, but not when you get to when you get to college. University level, mass starts getting quite weird, and it gets quite scary, really. And here you go to the Wikipedia, and you'll find this. You'll find that mass is not the same thing as weight, okay? Even though mass is determined by measuring the object's weight. Okay? They're kind of weird because, mass is not weight, but we determine mass through weight. Great. And then they continue, in physical science, one may distinguish conceptually between at least 7 different aspects of mass. or 7 physical notions that invoke the concept mass. So it wasn't as easy as in high school, was it? I mean, in high school it was easy. Quantity of matter were done. And boy, as we studied mass and other things a little deeper, especially the mathematicians, these people who call themselves mathematical physicists, and that physicists is with quotations, the concept, the notion of mass has changed radically. And the question is, then what are they talking about when they say, for example, that a black hole has infinite mass or lots of mass? What does a black hole have? It'd be nice if they would define this mass thingy or point to it if it's a thing so that we knew what they were talking about, right? And, one of the common notions people have is that you can take, for example, one thing that they did, take a hammer from the Earth. It weighs so much here on Earth. You can take it to the moon. It's got a different weight. And they claim that the weight changed, but the mass remained the same. Well, I got a problem with that because they just said here, they're going to determine the mass by weighing. It's not quantity of matter. We're not counting little atoms there. We're not counting units of mass. Okay, the way you determine mass is by weighing. In fact, for over 100 years, we had the Legrand in France, and that was the standard for the kilo, the Legrand kilo. And this was the 1 kilo, the standard. Every standard in the world was measured against that standard under certain conditions. Now they've got a new standard since the year 19, okay, 1 year ago. But the issue here is that, the grand kilo has so much matter in it. And you can say, well, that's the mass. That's equivalent to 1 kilogram. But how did we determine that? Well, we put it on a scale and weighed it and say, there's your kilogram. We didn't count atoms. We didn't count units of mass. Counting is different than measuring. Okay, two different things. Counting, you get a number at the end of the counting. Whatever, 1 gazillion atoms, fine. So you put 1 gazillion. Measurement is something else. Measurement, weighing, that's a totally different activity. And so you cannot compare measuring against counting. And it turns out that both mass and weight are determined through weighing, through measuring. Neither one is determined through counting. Okay, so that's important to make that distinction. So we have no difference between mass and weight until the mathematicians can figure out first what mass is, and then they can do something that separates mass from weight. Right now there is no distinction between mass and weight, as so many people say, because the way we determine mass is through weight. We weigh it. Okay, so that's the first issue. And yeah, here you have the standard hammer and feather experiment done on the moon. And they say, well, these two have different masses, but they have the same weight. Why? Because essentially they fall to the Earth at the same time. Okay? And so obviously it was not, if you look at the structure of the feather against the hammer, and you could have put an elephant there as well, it wouldn't have mattered because they would have both fallen at the same time. The issue is whether they have different mass. And you would intuitively say, yeah, they have different mass. They've got different, like the hammer's got metal in it, for example. And, when you hold it in your hand, it weighs differently than the feather. Here on Earth, at least, right? Maybe not over there when it's floating in your hand, essentially. So they say it has different mass. Yeah, but what do you mean by that? Do you determine it by feeling it, by weighing it? Is that how you determine mass? Well, that's weight. So how did you determine that the hammer has a different mass than the feather? if not by weight? Okay, and people have a lot of answers, but they never hit that one on the nose. They never are able to answer that question. As hard as they try, I don't care how many years they study at the university, as of today, no one can tell you first what mass is, and second, the difference between mass and weight. And so there's the first homework for you. Okay, go and figure out in fine detail how you're going to determine that mass is different than weight. And please don't give me the party line, because that's already failed. You got to invent something new. You got to come up with a new explanation of what mass is. First a definition, and then how you determine that mass is different than weight. Okay, and again, here you have it on Earth, just in case for those flat earthers who don't believe we went to the moon. Here you have, on the one hand, the metal and feather. They fall at the same time. Why? Because there's no air inside that box. Whereas when you put them side by side, you can see what's happening there, with and without air. Okay. Okay. With air, if the feather floats, and without air, the feather doesn't float. Okay. Okay. So that's the first issue. We have no idea what mass is, and we have no idea what the difference between mass and weight is. And so we're starting off on the wrong foot with this particle of mass. You know, it sounds more or less like, I don't know, the particle of love. I wish there was one. I throw it all the 18-year-old girls, you know, here, wham, wham, just bang them, they love me. Particle of love. And this is more or less the same thing. What is a particle of mass? Particle of a concept? It's like saying particle of weight. What sense does that make? And that's essentially what these people did, okay? Okay, an issue related to this is whether the photon has mass, okay? And you'll see why, because this is what's going to lead to the Higgs boson. They're going to try to figure out because of this problem, okay? So let's start here. What is the mass of a photon? Well, the physics fac frequently asked questions from the University of Riverside in California. And they have this. You can look it up. I've just chopped off a little bit of it. And says, does a photon have mass? After all, it has energy, and energy is equivalent to mass, right? E equals mc squared. Okay, there's a relation there between mass and energy. Straightforward, okay? And so they have this equation there. You can look it up in more detail. I'm just going to go through this quickly. And I'll look at that last one there. E squared, which is energy squared, is equal to P, which is momentum squared, C squared, velocity of light squared, plus, okay, the rest mass, m squared rest, sub rest, that's the rest mass, times velocity of light squared. So we have two situations which they analyze. They say if P is equal to 0, right, that little P in the red box there, P times C is 0. So that whole thing in the red frame goes to 0. And E is equal to the square root, because the square goes as square root on the other side. Okay, E equals square root of m squared, the rest mass squared, and a C to the fourth. Okay, and that you take the square root of that, and it's rest mass times velocity of light squared, which is the formula for Einstein's famous equation, E equals mc squared. The other scenario is, let's assume now that that the rest mass is 0. Okay, so we have now the m squared, what's in the green box, m squared sub rest. Okay, that's the rest mass. If that goes to 0, right, then that whole thing in the green box goes to 0, okay? And E in that case is equal to momentum times the velocity of light squared. So no matter how you look at it, okay, you end up with something. Whether the rest mass is 0 or the momentum is 0, you end up with something, because the other factor is the one that will give you a greater than 0 value. Okay, that's what they're saying. Okay, I hope you understood that. It says when the particle photon is at rest, its relativistic mass has a minimum value called the rest mass. See, they don't say it has 0 value. It has a minimum value. They don't clarify that. I mean, what is minimum? Minimum is like 0 or like 1? It's just a minimum value, so they don't clarify that, okay, and very conveniently. As the particle is accelerated to ever higher speeds, its relativistic mass increases without limit. Okay, so after doing all this gibberish, this mathematical nonsense, does a photon have mass or not out there? That's what we want to know. I mean, are they playing here? Are they saying it's got both? Whenever we don't need the mass, we say it's got zero mass. And whenever we do need it to have mass and we say it's got mass, we call it relativistic or rest mass or whatever, we just give it a name, and they have these different masses. Again, Wikipedia says there's 7 different notions of mass, and you don't know what they're talking about after a while because you don't know, the context changes. And so they say, oh no, here mass is something different. Here it's relativistic mass. Over there it's rest mass. And here we're talking about special relativity, and over there we're talking about general relativity, and over there about quantum mechanics. It's like every discipline, every branch of mathematical physics has a different value for the poor little photon. So we don't know how much it weighs. Does it weigh 0? Does it weigh greater than 0? We still don't know. Okay, so here they continue with that a little bit, and here's just a pictorial version of that. Here the elephant's running at slow speed, so he's normal. But now, if he ran at great speeds, he increases in size. That's what these people are saying according to relativistic mass. Okay, elephant goes slow, he's the same size. He doesn't increase in size or whatever. It's when the elephant, starts running fast, like close to the speed of light, that he grows in size. Somehow he picked up mass. Did he pick up more atoms? Is that what special relativity is saying? That when something travels at near speed of light, more atoms are piling up on them and they're growing like bigger and bigger and bigger? Certainly it's in opposition of length contraction, which happens also near the speed of light, where things get flattened out or shortened. So we get like, what do you mean that when we run at close to the speed of light, which is what special relativity claims, you have an increase in mass? What has increased? Are you talking about the weight? The weight against the scale? Is that what they're talking about? Are they confusing mass with weight? Keep that in mind. Okay? Anyways, I like the ending point from the physics fac at the University of Riverside. It says light is composed of photons. So we could ask if the photon has mass. Yeah, good question. Does it have mass? The answer is definitely no. Great. Could we stop there? No, we got to continue. The photon is a massless particle. Okay, great. According to theory, it has energy and momentum, but no mass. Okay, I thought energy was mass. And this is confirmed by experiment within blah, blah, blah. Okay, even before it was known that light is composed of photons, it was known that light carries momentum and will exert pressure on a surface. Yeah, it's known as weight. Okay, this is not evidence that it has mass, since momentum can exist without mass. Okay, yeah. So we have a nothing, we have a spirit that's pushing up against the scale. It's got momentum, but it has no mass. That's what they're saying. Sometimes people like to say that the photon does have mass because a photon has energy. Okay, where H is Planck's constant and F is the free, okay. Energy, they say, is equivalent to mass according to Einstein's formula, okay. They also say that a photon has momentum, and momentum is related to mass by P equals mv. Okay, fine. What they are talking about is relativistic mass, an old concept that can cause confusion. No kidding. The photon has no rest mass, but does have relativistic mass. The use of relativistic mass makes it much easier to describe the mass changes that happen when light interacts with matter. Yeah, because they want to use that specifically for special relativity, where they accelerate something at close to the speed of light. Continuing here, relativistic mass is a measure of energy of a particle, which changes with velocity. Again, it sounds like they're confusing it with weight. Okay, because if you're going to move something, you're talking about different locations. Weight is location specific, not mass. They say that mass, what was the quantity of matter? Well, obviously, they're not using the notion of quantity of matter here at all. So by convention, relativistic mass is not usually called the mass of a particle in contemporary physics. So, at least semantically, it is wrong to say the photon has mass in this way. But you can say that the photon has relativistic mass if you really want to. Oh, great, so everybody can say whatever they want. In modern terminology, the mass of an object is its invariant mass, which is 0 for a photon. Okay, so I hope you understood all that and are ready to take the test. Does a photon have mass or doesn't it? I don't care about relativistic mass. I don't care about inertial mass or rest mass. I want to know if it has mass. No adjectives in front of it, please. Does it have mass or not? And they're going to say, well, which mass are you talking about? Again, they have 100 different types of masses. They have not defined the word mass, and they conveniently left it that way so that, they can say whatever they want. Does it have mass? Yes, over here. And over there, well, no, it doesn't have mass. So what have we learned? They've covered all the bases by not defining the word mass. See, if you take Newton's equation, they run into trouble because it was mass divided by distance squared. Straightforward, quantity of matter. That's not the case. And they had to make amendments to prop up special relativity, especially that one. Okay, so we started out on the wrong foot. We don't have a definition of the word mass. We don't know the difference between mass or weight. We can't tell the difference. They say some gibberish there, definitions, but they always weigh the mass. They always weigh to determine mass. So all we know is that it weighs differently. They have never were able to isolate the quantity of matter, rest mass. The quantity of matter, what is that? Rest mass. The object is just standing still and you're counting how many atoms it has. It has 1,000 atoms, just to make it simple, 1,000 hydrogen atoms. Okay, so it weighs 1,000 units of mass. That's not what they do. They weigh it and they say, well, we don't know how many atoms it has. It just weighs so much. Well, that's weight. And if you send it faster against the scale, which is what they do in special relativity, well, yeah, the scale is going to go, whew, it's just going to read a higher number. What have we learned? Okay. So we start on the wrong foot. No definition. We can't tell the difference between mass and weight. And then we have all these different relativistic and inertial and whatever masses out there that they invent every day. And then you don't know what a black hole has if it's full of mass. What is it full of? Okay, so what does this have to do with the Higgs? Well, here's where it starts. See? Here's where it starts. It turns out that I talked about it the other day a little bit, where they were trying to figure out where hydrogen was made. And they said, well, inside the sun, you do not have enough pressure, heat, etc., to create a hydrogen atom. I mean, we can create the higher level atoms, the heavier elements, right, inside the sun. Okay, so they have all these processes. But how about hydrogen, the building block that makes up everything else? So for that, they had to go to the beginning of the universe, to the beginning of what? Of the Big Bang. They said there you can find the pressures, the density, the temperature, the time. Okay, you've got pressure, every parameter that you need to create hydrogen, and that's what they were working on. Okay, and they said, okay, so here we go step by step. Quantum relativity physicists, quotations, sought the gut or the toe. What is the gut? Grand unified theory. At high energies, electromagnetic, weak, the W and Z bosons, right? And strong, the gluons, forces merge into a single force. That was shown by a couple guys three guys that won the Nobel Prize, I think 1979. And then what's the toe? The toe unites that plus gravity, especially the graviton. Okay, so they try to merge and create a single force that underlies all of them. That's the notion behind the toe and the gut, really. Okay. So what happened? At the Big Bang, the temperatures, the energy, density, time, all that, they can produce hydrogen atoms according to what we said the other day. Hans Bethe and some of these other fellows worked on that, and they said we got an idea of how hydrogen could have started at the Big Bang, right after the Big Bang. Not exactly at the Big Bang, but like a couple seconds later, actually fractions of a second. Okay. So what happened? Okay, so atoms and neutrons, they're made of quarks. Okay, and so where did the quark come from? Well, it came from a process they call the quark epoch. Okay, in this region, also in the fractions of a second, the quarks were created from there. They assembled first into protons and then into atoms. Okay, so that's the notion they have. It all about special relativity. They say, well, that's another branch of science. We don't deal with that, you know. So yeah, the photon doesn't have mass. So again, you wonder, does it have mass or doesn't it have mass? Does it have momentum? Does it have energy? I don't care what it has. Does it have mass? That's all I want to know. A yes or a no would do, you know. It's a maybe. Okay, to this day, it's a maybe. Okay, so that was the starting point. They had to determine why or what caused matter to, especially the W's and Z's, which are particles which are inside the atom. Okay, so these particles are somewhere over there in the nucleus. You know, the nucleus used to be just protons and neutrons. Well, that's changed. You know, they put gluons in there. They put the weak and the W's and Z's in there as well. All these little beads, grains of sand between these monsters called quarks. Fine, okay. And when something happens, well, they shoot them out. Okay? And they call one the weak force, the strong force, the gluon are the ones that keep the quarks together, and so on. Okay, fine. So now we got to find out where the weak W and Z's came up with mass, whereas the photon, which was also apparently created at the Big Bang, or right after the Big Bang, microseconds after the Big Bang, how the photon ended up with no mass. These two ended up with mass, W's and Z's, and this one did not. And so this is the question they were investigating. Okay? So we got to keep that in mind, where all this starts. Okay, so here you see the evolution so that you can see it in graphic mode. Okay, here's the moment of creation, time 0 at 10 minus 43 second of a second. Okay, so here we're talking about seconds all the way to the green part almost. All that is less than a second. All that happened in microseconds. Like you see there, the quark epoch started at 10 minus 12 seconds. In other words, 1/trillionth of a second. Okay? So you can see this happened very fast, all this stuff. Okay? How did they figure all this out? Well, they calculated. How much pressure do you need? How much time do you need? How much temperature do you need? How much mass or fields or whatever do you need? And they did all these calculations. That's how they came up with all these things. It's just a mathematical calculation. And they get Nobel Prizes for this, for saying, hey, I figured out, you know, when the atoms were created, it was created so many microseconds after the Big Bang. And this is what these people study, and this is what they get Nobel Prizes for, and this is what so-called theoretical physics is all about, calculating this nonsense. Okay? And of course, they never deal with the moment of creation because creation is unknown. It's, you know, the latest they can go to like 10 to the minus 42 and so on of a second. And what happened before that, they don't know. After that, before that, I guess it's God. They can't explain the mechanism. They say it's unscientific because they can't prove it. They can't run an experiment. So go to philosophy and just do philosophizing all day long with them. So they have no explanation for the origin of matter. But they say we start at t plus 1, not at t equals 0. Okay? So that's important. They don't have an explanation for when it started. But they go through all this, all these calculations. Okay, in order to understand what the Higgs is and how the Higgs enters this process of determining why the W's and Z's have mass and why the photon does not, you need to understand something known as symmetry breaking. Okay, very fancy term, scary for some people. I'll try to explain it as simple as possible. You got a Mexican hat, okay, and it's rounded at the top. You put a ball there. Well, it's not going to last long up there. But as long for that microsecond that it's still up there, you can see that the hat, but you look at it from one way or the other, it's essentially the same. Okay, so it's symmetric. Now, if the ball rolls down, which it will, it'll fall down, in this case, on either the left or the right. It doesn't matter. If it falls on the left or on the right, you can see that the hat is no longer symmetric. Okay, the left-hand side is not the same as the right-hand side. Okay, that's called symmetry breaking in a nutshell. How does that relate to the Higgs? Well, when we were at these gazillions of microseconds, okay, there was this field. God, he made the field, the Higgs field. There's a proposal that there was a field, and all these particles just crashed against the field, and some interacted and some did not. Okay, so you got some particles which interact, have friction, they scratch their elbows against the field, and others that whiz right through it for whatever reason. Okay, and so the more you interact with a field, the harder it is for you to get through this molasses. The other one goes through water and the other one goes through air, so one goes faster than the one through water, and the one through water goes faster than the one through molasses. And what happens? The more it takes for you to go through a denser, or the more interaction you have with this field, the more weight, the more mass you have. In other words, they turn mass into a dynamic concept. It's no longer counting how many particles you're made of. You can see that it's got to do with motion, with you pressing up against something. And we all understand that notion. Of course, we understand the notion. Question is, what does it have to do with mass out there? I mean, are we talking about quantity of matter, or are we talking about how much pressure you encounter as you move through a medium? These are two different kinds of notions of what mass is. And again, what they've done is they've turned mass into a dynamic concept. It depends on how much resistance, how much drag you encounter. Okay? And what happened was this symmetry breaking occurred then. And you say, huh? What's that? Well, what happened was that until then there was no resistance. But when they encountered the field, the Higgs field, it broke the symmetry. They couldn't return back to having no mass. Now some had mass and others did not. Okay? So it broke the symmetry. In other words, symmetry is when something doesn't change with what is called invariant. Okay? You continue onwards without any problem. If something changes, then it's no longer invariant. Now it's variable, not varied. Something changed. What changed was they acquired this resistance that these people call mass. Okay? So again, what is mass? It's the resistance to movement, not the quantity of matter. Okay? Because quantity of matter, we don't need to move the object at all. It's what you truly call rest mass. You have the apple, you count how many atoms it's got 1 billion atoms. That's the mass of the, assuming they're all hydrogen, right? That's the mass of the apple. That's got nothing to do with throwing the apple, whether through molasses, through water, through air, through some medium, and it encountering different resistances or different friction as it goes through these different media. Okay? So let's understand that first. So what was Higgs' contribution to this idea? Well, he created this mechanism, this C. He's one of the guys. There were several people working on it. He got the credit. I don't know why, but this is the notion. Okay, you have more particles some particles interacting with this Higgs field. And the more it interacts, the slower it goes, well, the more mass it has. That's essentially what these people are saying. Okay, very simple concept, very irrational. Okay, very irrational, because what does this have to do with why you weigh more on the scale every morning after you've eaten? Are the particles pressing down on the scale more? I thought when you eat, you weigh more because you put more matter in your body. And these people are saying, well, yeah, that's the notion of high school. That's not mass at the university level. University level is a lot more complicated. I see. Yeah, no kidding. Okay. Here's because now we have to explain why. Why is there a difference between why doesn't the photon have mass and why do the other two have mass? So here we have the super duper scientific answer, which is several of them. First guy, and all these are authorities, okay? By the way, I took this out of only people who are physicists, who are really deep into all this math, etc., right? The Higgs does indeed interact with a photon. In other words, one guy says, yeah, there is interaction between the photon and the Higgs. Well, then why does it not have mass? And they say, and sometimes they'll tell you that the photon sometimes interacts with a Higgs field. So I guess the photon sometimes acquires mass and sometimes doesn't. I don't know. These people say whatever they want, and nobody even checks them. They just send them the check, their salaries, their grants, their Nobel prizes, their medals, and nobody questions these things. The Higgs field is not electrically charged. Oh, that's one answer you'll find out there. And why not? Well, photons only interact with electromagnetic particles, such as protons and electrons. But it turns out they also interact with neutrons, because neutrons reflect photons as well, which are not electrically charged. And we know for a fact from general relativity that also they interact with gravitons, because relativity states that gravity bends light. So we haven't answered the question. Saying that the Higgs field only interacts with what is electrically charged does not tell us anything, because there are particles which, like neutrons and gravitons, which are not electrically charged, and they're alleged, the graviton, they're all alleged to have mass. So we haven't answered the question. But he got the Nobel anyways, okay? He got the little medal anyways. It's just a property of photons, similar to properties of other particles like electrons or protons having a charge which is their property. It just is so. It is so. God said, and it is good. That's it. There's no explanation. So he hasn't answered the question. He just came up with a mechanism, says, hey, I can explain the origin of mass. It's this river of molasses, and some particles can whiz through it and some cannot. And the ones that cannot have mass. That's all they said. They still can't tell you why the photon particle goes through that same molasses and doesn't have mass. It just whizzes right through. They just say it is, but they can't tell you why. What's got this particle got that all the others don't have? And the best answer for, if you're going to take the test, is just put all of the above. You're probably going to get it right anyways. It doesn't matter which one you answer, which A, B, C, or D. So you might as well just put all the above. So that's it. It doesn't get any better than that. But it doesn't stop there, because you wonder, well, why did this fellow get his Nobel Prize? I mean, yeah, anybody can come up with a theory and say, well, yeah, there's this river of the Higgs field out there, and everything that goes through it, well, different particles have different amounts of mass. Yeah, that's a theory, okay? There's the proposal. Why would this guy receive a pat in the back for this? Well, it turns out that, they went out there and they proved it. You need proof in mathematical physics, otherwise it doesn't hold. And so, let me get this. No, wrong one, sorry. Here's the LHC. And what they did was they accelerated particles, especially protons. In other words, they removed the electron from the hydrogen atom, and they claimed they accelerated these ions, and they made them crash against each other. Okay, and after they did that, okay, so they were able to analyze the debris, you could say. Okay, and so here's the debris. Okay, more or less what they think it might look like in there. This is all obviously done with computers. It's not actual filming. Okay, so let's keep that in mind. And okay, so they have they watch this. They simulate it, and they say, okay, this is what we observed, and they actually it looks more like this. Okay. Okay, so it looks like fireworks, collision, and little squiggly lines. Here they're straight, but they're really squiggly lines that come out of there. And they look at those squiggly lines and they say, oh, those are traces of particles escaping from ground zero. That's their notion of this. Okay, and by doing so, they were able to locate a little blip in the chart. And they said, hey, that's the Higgs. That's the one we predicted for the Higgs. And that's the right mass of the Higgs, which was 125 gigaelectron volts, the energy needed to accelerate a particle. And they have all these weird notions where, you have a tiny particle, such as a quark, which weighs more than the gold atom that contains the quark. So you explain that. That makes no sense whatsoever. Why do they have that? Because it's the amount of energy they need to accelerate something. And then they say, well, energy is mass, and so that's the mass of the particle. And so if you need more energy to accelerate a quark than you need to accelerate an atom, then the quark, which is part of the atom, weighs more than the atom. It's like the seed of the apple weighs more than the seed that contains the seed. Weighs more than the apple that contains the seed. You figure it out. But this is what these people come up with. Okay, so here's what they gave Mr. Higgs the medal for. It says, for the theoretical discovery of a mechanism, the Braut-Englert-Higgs mechanism. And they raised the first two names. They just left it as the Higgs mechanism today, essentially. The other guys got the medal. Well, not Braut, he died, so they had to hurry up because these people are very old. They're close to 90, all of them. And so they say, well, before the next one dies, we better give them a medal because otherwise we'll lose the chance to give them a medal. And that's another thing with gold medals at the Nobel Olympics. And that's that, they have to give it to the old folks before they die because they don't give medals to dead people, okay, at the Nobel. It's not, you don't give them retroactively, like maybe the Iron Cross or something like that. No, it's got to be to a live person. And so these people were close to their 90s, said, we better give them a medal before they die. One of them died. In fact, here I have this other fellow. If I can find him. Here he is. And his name is Francois Englert. And the other fellow was Braut, he died. And so they gave him what? What did they contribute? To our understanding of the origin of mass of subatomic particles, and which recently was confirmed. This was the key issue. Was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN Large Hadron Collider. Okay, so yeah, they came up with this notion, and that there's this river, and particles swimming through the river have different masses according to how much resistance they find. They can't answer the question of why the photon does not have mass. They don't have a definition for mass or the difference between mass and weight. And so what do we know today? Well, we know very little. That's where it all ends, more or less. So I don't know. You figure it out. You've got time to think about it in your dark basement. Okay, Let's do some comments here. See if we can get these comments in the right place this time. First comment here, or question, fellow says, he says food, referring to me, he says food or something will cause the extinction. That's not why a hunter-gatherer would become extinct. Hunter-gatherer did use trade to eat. Correct. Hunter-gatherers did not use trade. And what we need to clarify here is what escaped him, this fellow, is that there's two mechanisms. One is the one on the left, the other one is the one on the right. The one on the left, two examples there. One is the mouse utopian experiment done by, what was his name? John Calhoun. And that was a background extinction. And it's got to do with several factors, as far as I'm concerned. And one of them is aging of that population. The other one is the fact that they lose their genetic diversity. And of course, what happens is the population pyramid of that group overturns. And that's what happened to the mice that Calhoun, the experiments he did with mice and rats as well. And then on the bottom you see there the world population growth rates for humans. And we're going down to zero. Okay, we're going to have zero population growth sometime this century. We're not having kids, we're not having children, and at least at the rates we had in the past. So our population is going to decline eventually, because once we get to zero population growth, that means now the total population on Earth does not increase. And from there, we only have three possibilities. It either increases, stays stable, more or less, or comes down completely. And then on the right, you have the mass extinction. What is that? Well, that's when food disappears. So these are two different mechanisms. The Neanderthals, which died in a background extinction, followed what's on the left. Whereas I predict, I'm saying that's going to happen. We're going to fall because we're going to die like the dinosaurs in a mass extinction. Okay, that's my theory. Okay. It's not a prediction, really. It's a theory, because the theory is that animals in the past died because of this mechanism. So I'm referring to the mechanism. And we cannot escape the same mechanism that claimed their lives. And this is like, I'll give you an analogy, because some people question that. And here's the analogy. Analogy is the eclipse, a solar eclipse. So you have the moon go in front of between the Earth and the sun, okay? And I tell you that we're going to have a bunch of eclipses in the future. And you say, well, are you making a prediction? No. What I'm doing is explaining. What am I explaining? I'm explaining why we're going to have, in the future, we're going to have eclipses. And I base that on my experience. And I'm saying, look, in the past, we had the moon go in front or in between the Earth and the sun, and that's what caused eclipses, and it's going to happen again because the moon is just going around and around and around. At some point, it's going to get between the Earth and the sun at the right place at the right time. It's going to happen again. So I'm not doing a prediction and saying that necessarily that it's going to happen tomorrow at 2 o'clock. No, that's not what I'm saying. I'm saying here's the mechanism of why we see eclipses. Okay, and why they will continue to happen in the future. And this is more or less the same thing. We're not saying here, hey, on the 5th of March of, the year 2030, the last human's going to die. That's not what we're saying. We're saying, look, there's a mechanism that caused the extinction of animals in the past, and we, humans, cannot avoid it, so it will happen in the same way. It's got nothing to do with predicting. It's got to do with explaining a mechanism. Okay, that's the context, and not everybody tunes into that. Okay, another issue here raised by a fellow. I think the same fellow says, what will cause the extinction won't be a lack of resources, but no trade. Okay, it's not going to be a lack of resources. Well, in other words, it's not the lack of resources that's going to, according to the theory I have that I'm proposing, that's causing the extinction of man. Not in a strict sense. We can produce as much food as we want as long as we have an economy. The economy is what produces food. In other words, we have this thing we call money. Okay, this abstraction. Usually today it's not even money like real paper or coins. There's less and less of that. What we have out there is a bunch of numbers, just an abstract world of quantities. And these get passed around from account to account. So we have this accounting system. And that's what makes the world go round, because thanks to that, there's a group that specializes in producing and distributing food to all of humanity. If that accounting system happens to fall apart, then this group that produces and distributes food no longer has any pecuniary incentive to continue doing so, to distribute, to produce and distribute. So that's the theory, okay? And so, once that happens, there won't be any trade, because the mediator, what we use to exchange, is what disappears. Right now, we have no problem because everybody accepts money. But when the economy collapses, what I'm saying is money disappears. Money is no more. And in that case, what held the whole system together, this abstraction we call money, is no longer there to serve as a mediator, as the currency, as what we trade. Because we don't really trade apples for oranges today. What we do is we transfer money, we transfer funds, we deal with credit. So this guy has so much credit because he bought so many things, or produced so many things, or sold so many things. And so everybody's got his little, pile of gold. And that's what they exchange. And we all accept that right now. But what are we accepting? An abstraction. So yeah, it's very easy to destroy the human economy because it's all abstract. It's all based on faith. The fact that what is it? In God we trust. That's why it continues rolling. All we have to do is lose faith in God, and you lose faith in money. That's it. That's the end of the world. Okay, so that's the theory. Okay, here's another question or comment. Fellow says, what about AI robots? They could explore the galaxy for thousands of years. If we made some and released them, they could roam long after humans are gone. Well, the first issue with that is that we're out of the picture, because humans are not robots. So the fact that, assuming, best case scenario, that we manufacture robots, intelligent, whatever, that can do a lot of stuff that we can do, in other words, essentially human, but they're robots, they're made out of tin and, nails and screws and whatever. So this robot can do whatever it wants, fine. Okay, so the robot goes out there and can go to another planet or to another star system, whatever. That's not us. Okay, we're gone. Our species is dead. Okay, that's the first issue. The second issue is we're never going to make it to making robots to such sophisticated levels, because our time is up. We're about to go. So we won't even get to, make the ships that these robots will have to use to get out of the planet. That's assuming they're made. Right now, we can't even make these robots to the fine point where they can replace us. Okay? And I know a lot of people have problems with that because they're in the AI age, and they think that, artificial intelligence, that's going to conquer the world. No, it's too late for that. We're on the way out, and the robots can't catch up with us, no matter what they do. And so all I can tell you is, my 5 cents worth. That's the way I see it. I don't think robots are ever going to make it. It's a nice toy for playing around, for getting things done, and say, I'm going to use the robot, fine. But I don't think robots have any merit whatsoever as far as especially interstellar travel. Okay? In fact, what are they doing with Mars? Are they sending robots? Well, we already did that. We sent a little R2-D2 over there. He roamed around the planet and sent information back. That's it. Now we're sending humans. Okay, and I don't know why they're sending humans, because are we going to colonize? Are we going over there to explore? Are we going there to evacuate the Earth? What are we going to Mars for? Smaller planet, no air. We would have to create the air over who knows, engineer it for who knows how many thousands of years to create air on a planet that is smaller than the Earth, that has less gravity, very little magnetic field. Are we going to live there? I say no. Never going to happen. And we're not going to make it on time. In fact, the global economy, I think, will collapse a lot sooner than that. In fact, it might collapse 2021. It might be our last year, for all we know. Okay, here's another issue a fellow raises. He says, well, problem with that is the fact that scientists literally got a picture of one this year. They're talking about black holes. He's saying that they got a picture of a black hole, and so that here I was saying that there are no such things as black holes, and say, well, we got a picture of it. How can you deny that? It's like saying, what do you mean there are no unicorns? We got a picture of a unicorn. Well, is that a picture? Or is that a collage? Is that a computer-generated collage? What is that? But more important than that, or more fundamental than that, we don't know what a black hole is. So what we do when we don't know, we go to authority. And here we have the greatest authority that ever lived, especially on black holes. His name is Stephen Hawking. He died a couple years ago, and he said the following. He said, pointed this out in the past, Eddington thought it was simply not possible that a star could collapse to a point. Einstein himself wrote a paper in which he claimed that stars would not shrink to, what? Zero size. Zero size. Now, does that thing that's on the left, does that look like zero size? I mean, it looks like it's got at least 2 dimensions, if not 3. And so, that's not a black hole according to what a black hole is supposed to be. A black hole is supposed to be zero size. And that thing on the left is not zero size. So I don't know what they took a picture of. This is the first issue. It's got to be addressed. And so, yeah, no, that what you got to first do is define what a black hole is. Then you can tell me that's a picture of a black hole. Right now we don't have a definition, or we don't know if it's an object or a concept, a black hole. So we don't know what it is. What is a black hole? And until we get a notion of what a black hole is, well, first, whether it's an object or a concept. If it's a concept, it's irrelevant. And if it's an object, hopefully it's not zero-dimensional, because if it's zero-dimensional, it doesn't qualify as an object either for the purposes of physics. So far, we have nothing. So, no, that picture is meaningless, showing again that experiments will not make a zero-dimensional entity, if you can call it that, go on a photographic plate. There's no way you can get it there. Okay, so no, I don't know what that is. I'd like to know one of these days. Okay, another question, comment. Fellow says, sounds to me that hydrogen is not what makes a star, but instead is itself produced in the star as the first step of the fusion process. I can't help but wonder if a star is a process formed by the coalescing of unimaginable numbers of electromagnetic ropes from and to all angles. A star which appears to us as a ball of plasma is really a dense spot of ropes. Okay, that's a different take. I have no problem with new ideas. I don't subscribe to this, but people should kick all ideas around. He's saying essentially, I guess, that the sun is a big neutron ball where all the ropes just crisscross and have this thing called the sun in there. Maybe that's one idea. I personally don't subscribe to this. Let me tell you what I subscribe to. I subscribe to essentially to the mathematical physics version of how a sun works, how the star works. In other words, I think it works through fusion, just like they say it does. I think that one they hit on the nose. I think, but there's a difference, okay? And there's a difference between what they propose and what I propose. What these people are proposing looks something like this. What you have is, if you go inside the sun, center of the sun, according to them, all these particles are traveling at great speeds, way in the center of the sun. And so they're colliding against each other. And when they collide with the right speed, with the right pressure and temperature and whatever, that's when they form higher level elements. This is their notion of it. This is not my notion of how a star works in the center. It works through fusion, but we have a different notion of what fusion is. Okay, and here's my version. My version is that all these things are compressed. There is no motion or very little motion inside the sun. What you have is pressure, extreme pressure, gravitational pressure from everything outside the sun pushing inwards towards the center of the sun. So I don't have this notion that these people have of traveling particles that collide at great speeds. See, this is what they think they're doing at the colliders. They're saying, look, we sent the, like we just saw with the proton, you have the hydrogen atom you remove, supposedly that's what they think they're doing. They're removing the electron, so now it's positively charged. Now they can accelerate that with a series of magnets and, kind of make it into a pinpoint, a very thin pencil. And then they say, well, they take the two beams, one going in one direction, the other one going in the other direction, and they hit the two beams face on, head on, one against the other. That's what they think they're doing. Okay? Now that's different than what I'm proposing. I'm saying that what all these so-called protons being accelerated are really is a continuous, okay, series of atoms which are bound to each other. All the electron shells all around the accelerator are connected to each other. And so they have them spinning in place. There is no acceleration of a little particle. What they have is all these things are torquing, these serpentines, as I call them. And what they do is they put one serpentine going clockwise against another one going counterclockwise, and they put the two tips one against the other, and that's when they create these loops, which are the threads. That's what they are. And these threads have the potential, not the potential, they actually do, hit the gases inside the chamber, and it's the gases that move, that create these lines, which they later are able to simulate with their computers and say, oh, here's this curved line, and we're going to call that Joey, and this one we're going to call Tommy, and this one we're going to call Johnny. Okay? That's the way they work, and they think they are traces of particles. And I'm saying they're not traces. What they're doing is they're rubbing two serpentines, one clockwise, the other one counterclockwise, against each other, point against point. And when they do that, it's like if you take two drills, and one's drilling in one direction, the other one in the other direction. Well, if they're going fast enough, you're going to get some sparks out of there. And that's more or less what they're doing at the accelerators when they supposedly collide particles. And what happens is, out of that process, what you have is these threads, which are now thrown in disarray in different directions. Those are going through the gas that's in the chamber, and that's when they can see these traces, so-called traces. What they are is really the thread going through the gas, and they are able to simulate that with their computers and say, oh, here's a trace. No trace. And what's happening inside the sun is the same thing. There is no collision. What we have is particle against particle being compressed, one against the other, under extreme pressures, more and more, until finally they fuse 4 hydrogen atoms to create 1 helium atom. See, you got to look at what the helium atom looks like according to these people. And it looks something like this. And you say, is that a ring? No. That ring that you see there, that's a trace. That's a contrail. Mighty Mouse's contrail, he flies through the sky and then envelopes or ties up the cats with it. That's the same thing. That's not a real thing. They have to put it there because otherwise you wouldn't make sense of what you're staring at. So they always put the little circle, which is the trace left by the electron. And they call those orbitals. Why? Because it's a bunch of orbits. That's why they call it orbitals. All we're talking about is motion. And what they're doing is all these contrails, they bundle them up and they say, okay, we have an orbital. What is an orbital? A bunch of orbits. And then they start binding the orbitals, the contrails, from different atoms. Yeah. Now we're saying those are balloons. Those are membranes. And you push one against the other here. Let me show it one more time. This is the notion that we're proposing. All these balloons are being squashed against each other, and with enough pressure, you can get 4 of them to make up the next level atom, which is helium. Okay. And from there on, you can get even, more heavier atoms out of that, heavier elements. So we have a different version, and I'm saying the sun, that's what a sun does. So in a sense, I do agree with them. It's a fusion process. Where we disagree, it's not a banging, it's not a collision. It's a compression, just pressing. It's a different mechanism that when they're proposing. The reason they propose theirs is because they think they're accelerating particles in their accelerators, and that's how they create higher level elements. I'm saying that's not what's happening. I'm saying that what they have is these serpentines, which are touching each other, one going clockwise, the other one counterclockwise at great speeds, and they put them together like 2 drills, and they get these sparks. And they say, oh, particles. No particles. Okay, another comment here, another issue. Bill, you can't prove a globe. We have a flat earther. Okay, love those guys. They come in with flat earth stuff. And, this is for the gazillionth time now. I wish some of these guys would stick around to find out, what I'm answering. And here's the first one, okay, and what you see there is an atom which is connected to all other atoms in that sphere. It's supposed to be a sphere. And if that atom is tied to all other atoms and the other one is tied to all other atoms on the side and the one on the bottom, well then, everything tends towards the center of the sphere, and that creates a spherical object. Okay, and if you don't believe me, you can probably simulate this with elastic bands. You can probably tie a bunch of balls to a rubber bands, and you can create this effect. Maybe if you're careful enough. It takes a little while to build a little ball with this, but you could do it. And so here we have the Earth, same mechanism. Any atom, whether it belongs to the air or to water, is being pulled towards the center of the Earth, and that's why water does not fly out of the Earth, or why air doesn't float away, because every atom that comprises air, every atom that comprises the oceans, the rivers, whatever, is stuck to the Earth because they're all connected through electromagnetic ropes. We have a physical mediator that prevents that atom from flying out into space. And that's it. I mean, if you don't understand it, I can't help you any further. It's a kindergarten stuff. Okay, you just have to conceptualize it, visualize what I'm saying there. Okay, and here we have another comment or issue. Fellow says, please counter the content at, and he gives a website. Okay, you'll find it there in his comment. Okay. I'm sure you will be enlightened after reading it. Okay, I want to be enlightened. Always want to be enlightened. I go there and this is what I read. Just a couple things that I read, I pulled out of his site. It says, the theory is new. Whoa, new theory. Okay. The existence of dragged ether still is a scientific possibility. Ether, I've heard of that before. I don't think it's new. I don't know, have you ever heard of the ether? If you have, well, then this doesn't seem very new to me, Theoretical physicists cannot disprove the ether theory. Okay. So he wants people to prove or disprove. They rejected the possibility of ether because it differs too much with the present scientific perception. Okay. A relative simple experiment can be performed to determine whether ether exists or not. Well, the first thing we have to say is that, the mathematical physicists, they believe in the ether. Laughlin, Nobel Prize, he said, what we have in mathematical physics is an ether. We just don't call it that because it's taboo. So this individual is, not in tune with what's going on out there. Yeah, all they've had in mathematical physics for the last 3,000 years is ether. It's always been an ether. We never gotten rid of the ether in mathematical physics. Okay, so I don't know what he's talking about. Okay, so here we have what? Here we have what the ether is. There you see the ether, a bunch of particles. That's what ether is. It's a background of particles that supposedly fill space or is space. Some people say it is. Some people say it just fills the container called space. Okay, fine. And here are the answers. The ether has been around since the days of the Greeks. In science, we don't prove theories. Ether is not a theory. Ether is a hypothesis, an assumption. Okay, ether is alleged to be an infinite body of particles. In physics, we don't determine whether your God exists through an experiment. So forget about doing an experiment to prove or disprove. In physics, we define the word exist. Then we know whether your ether or your God or whatever exists. If your God meets the specifications of the word exist, your God exists by definition. So all you have to do is define the word exist. So please don't run any tests. Don't request any tests or experiments. Please define the word exist so we know what you mean when you say exist. Okay? And no, the ether has been debunked, even though mathematical physics continues to use it, but they don't call it that because, again, it's taboo. But it's been debunked in the sense there is no ether. It's space, and space is nothing. What is nothing? That which has no shape. Something is that which has shape. So we have two antonyms there, and now we can use them consistently in a discussion. First, you got to get the language right. Then we can talk about existence, ether, space, or whatever. First, we need to get the language, because right now we're not communicating because you don't have definitions. I have my definitions. You don't have to agree with them. You have to fight for them. You have to defend them. Sword and shield, get in the ring, fight it out. You can't just say, well, I disagree. We don't care if you disagree. And science is not about disagreeing. Science is not about opinions. Science is about explaining. For that, you need to define your terminology before you get in the ring. Okay, last question or comment here. Fellow says, the rope hypothesis, which they stole off me. Okay, I stole the rope from this poor man. Okay, but he says, right after then, a little while later, he says, I pointed out some of the flaws in some of his theories, meaning my theories, right? Such as magnets. A rope swung around you like a jump rope will tie you up because there isn't a ball joint, as there are in jump ropes. The nature of a rope, and I've done this, will tie you up and wrap around you as it twisted around your body. Go get a rope and jump it. Well, first of all, you can't attack the rope model on the basis of tangibility. Okay, because I'm on record saying that the rope is intangible. You cannot touch the rope. So the rope that we use in everyday life, the one you buy at the hardware store, the only similarity this has with the electromagnetic rope is its format, its architecture, its structure, its configuration. That's all it has in common. That's why we call it a rope. And it's also a physical object. The electromagnetic rope is a physical object like this one. This one, you can't have the rope go through. If you try to get one rope to go through the other, you can't do it. Not here in our macro world. In the electromagnetic rope, yes, it goes right through the other because it doesn't have the property of touch. It does not have the property of tangibility. And for sure you cannot see it because, if an atom, we can't see an atom. You can't see like a hydrogen atom. We can't see it. In fact, they can't see any atoms except like from a bird's eye perspective. And so they say, oh, we've seen atoms. We've photographed atoms or we imaged atoms. No, it doesn't count to do it from 1,000 kilometers away. No, we want to see the little electron going around. That's what we want to see. And you'll never see that because, they can't get in there that that close. And so they say, well, see, we photographed atoms. And people say, oh, look, the scientists, they've imaged atoms. No, they haven't. Not what we need. We need to see inside the atom. We want to see that little electron bead going around the atom. That's what we want to see. And they can't get it like that. And so we don't know what an atom looks like, and these people can't draw it. I mean, if they photographed atoms, it's a simple deal. All they have to do is draw the atom for me. I want the hydrogen atom. I want someone to draw a hydrogen atom, the genuine one that they photographed. What does it look like? Is it a little bead going around the nucleus? Is that what an atom looks like? And then they have to explain why that electron bead doesn't spontaneously fly out of the atom. And of course, they can't do that. They just use it. They say they can't imagine it, but then they say they photographed it. And of course, if we have not photographed an atom, much less can we imagine seeing or photographing the ropes that interconnect two hydrogen atoms, which are orders thinner than an atom. You know, I mean, you're talking about if this is an atom, and here I'm being kind to the atom. If this is an atom, the atom would look like the Earth, and the thread that's connected to it would look like this. So you would not see the ropes or the threads. And again, these ropes and threads, they do not have the property of touch that we have in our macro world. So that's given with the assumptions of the theory. Okay, that's why it's called the rope hypothesis. And you don't have to agree with that and reach your own conclusions. All I'm saying, that's what I'm proposing. Okay, that Mother Nature has these objects out there that have no tangibility, no property of tangibility or of visibility, but they are objects. They are objects not because you can see or touch them. They are objects because they have shape. Okay, and as far as him having discovered the rope model, well, it turns out that he criticizes the rope model, but he says he discovered it first.